good?
Yeah.
All right. So it's a great pleasure to welcome Hadas Kress-Gazit here at U of T, at the U of T Robotics Seminar Series. Hadas is the Geoffrey Hedrick Sr Professor at the Sibley School of Mechanical and Aerospace Engineering, and also the Associate Dean of Engineering for Diversity and Academic Affairs at Cornell. She's also a leader in the robotics community, so if you've been to a robotics conference, you've either seen her or you've met her. Hadas received her Ph.D. in electrical engineering from UPenn in 2008, and she has been at Cornell since 2009. Her research focuses on formal methods for robotics, and more specifically on synthesis for robotics, and that is the automatic creation of verifiable robot controllers for complex high-level tasks. Her group explores different types of robotic systems, including modular robots, soft robots, and swarms, and synthesizes ideas from different communities such as robotics, formal methods, control, and hybrid systems. And as of late, Hadas has also invested significant time in thinking carefully and carefully about robotic evaluation. Hoping she was going to talk a bit about that as well. So she's an IEEE Fellow and has received multiple awards for her research, for example, the DARPA Young Faculty Award, the NSF Career Award, and as well as others. She also got an awards for teaching and advocacy for groups that are traditionally underrepresented in STEM, and she has spent significant time and effort leading the organization of important robotics conferences and also efforts to improve the culture in the robotics community overall. So, with that said, take it away. Welcome to your seat.
Thank you. Thank you. Thanks, Karen. That was very lovely. I appreciate it. Thank you. Okay, so shockingly, for methods for robotics. But before I actually start my talk, I'm going to use this captive audience to advertise two things. First thing I want to advertise, assuming actually this works. Let's see. Oh, there we go. Okay, cool. First thing I want to advertise is Cornell Robotics. So we have about 25 faculty that do robotics across two campuses, not quite as close as your campuses outside here. We have one in the main one in Ithaca, another one in Cornell Tech at New York City, across multiple departments, multiple colleges. There's a question mark there because we do have a search this year for cyber-physical systems. Me and Mark Campbell are going to be running that search. If you have interest in that, come and talk to me after. If you're not quite ready to be a faculty member, but either you are or you know undergraduates who are interested in robotics, we have a new robotics PhD that we're starting to admit this fall. So it's if you're interested, let me know. It's an interesting vehicle that we're doing. The application deadline is either December 1st or December 15th, depending on kind of the route you're taking. Again, happy to talk about that after. Okay? So please spread the word. I would love to have applications for both from U of T and other people. Great. All right. So my title was Formal Methods for Robotics in the Age of Big Data. And the older I get, the more I kind of think about the purpose of things that I do, right? Why am I doing this? So I'm giving a talk right now, and there are different kind of types of talks that you can give. You can either go into one specific result in great depth. You can give more a broad overview of a field. You can have more of a position kind of thought-provoking or opinionated talk. And I tend to gravitate, when I give talks in these kinds of forums, I tend to gravitate towards the breadth in terms of kind of, let me tell you a little bit about well, mainly my work, because, seriously, I'm giving a talk, but the lay of the land in terms of what things can be done with the type of approaches I'm interested in. And then, in this case, since I spent last year on sabbatical at Toyota Research Institute, I have some other thoughts that are coming in. So it's a little bit, it's going to be a combination, overview of a field, soapbox, call for action, and hopefully thought-provoking. So that's kind of what you should be expecting. Hopefully I'll be able to do that. So I'm going to spend a large portion of the talk on the formal methods for robotics. That is my research. That has been what I've been doing for more than 15 years. in different aspects. And my thinking, as one does, that my thinking on this field has changed over time in terms of kind of grow slightly more nuanced, I think, in your thinking, typically. So, formal methods for robotics. How many of you, well actually, let me not go there yet. So I have these words, formal methods. And I want to kind of, so I gave a talk last month at a formal methods conference, which is interesting because you guys, I'm assuming, are mainly roboticists and not so much formal methods people. And there I was giving a talk to formal methods people who are not roboticists, the vast majority. So kind of the nuances are different. But let me kind of set the stage in terms of what is formal methods. So I really liked this paper. This is a paper actually by the people who were at the conference for formal methods, which was really cool to meet them. I'll meet one of them. What is the definition for formal methods? So they wrote this paper, which is really fascinating in terms of, they basically asked people, how do you define it? What are the challenges? What do you think the success stories are? What is still not done? But they came up with this definition, which is mathematics-based techniques for the specification, development, and manual or automated verification of software and hardware systems. Great. Software and hardware systems, robots, right? Fits within that. Mathematics-based techniques, we kind of have that, right? And then there's some of these words of specifications, verification, development. What does that mean, and how do we think about that, right? So typically from that world, you have a model of a system. And then you can start thinking about writing requirements for this model, checking whether those requirements hold, and so on. And then you go to robotics, and you get things like this. Right? So this is the DARPA Robotics Challenge that happened in 2015. This is IEEE Spectrum put together a video of all the falls from the first day. This is a snippet of it. I love this example, because this example is supposed to turn the valve, and it grasps something, but it didn't quite grasp. There's a clear perception problem here, right? It thought it perceived something. A lot of kind of just stability issues, and this is also one of my favorite examples. This is actually out of MIT. There was something about kind of, wasn't quite in the right mode. It clearly fell. It actually did get the point for egress of the car because it had to leave. It had to end up inside the yellow square, which it did, okay? So to be fair, that was actually a really great example of wonderful algorithmic development because the right arm broke, and they were able to do most of the mission with the left arm, even though they developed mainly for the right arm. So this is a really, I mean, I don't think this was the outcome they wanted, but it turned out really well. So why am I showing this? Robot falling is a good way to start kind of a talk. The other thing is that the mathematical models didn't predict these things. Right? The perception failure, that was kind of a bad perception failure, right? Especially given that there was human in the loop. That's a different conversation. But robots are hard. Robots fail, robots fall, robots, having a mathematical description of this thing, that's hard. In addition, we have people. So this is I don't know, how many of you have seen this video? Okay. So this is a HRI paper from 2015. Researchers in Japan put a robot in a shopping mall and basically left it there. Turns out, kids can be mean. And they prevented it from moving, they kicked it a little bit, there's a whole bunch of things, not great behaviors happening there. So again, I'm showing this video in the context of verification and specifications and all that. So there's other things, when we think about robotics, especially these days, we think about robots with people, around people, working with people. And these are people, young people, but people. So you don't even have to go to that extreme of, the kids are just having fun with whatever the toy design tells them. A different example is, this is work from who's a faculty member at Cornell. He does a lot of work with assistive robots. So this is in the context of feeding. So feeding people that have motor impairments. So they can't move, or they have some spasms, or things like that. And then feeding them. So that's this is autonomous robot feeding them. But you can see that the questions of verification become a lot more, I don't know if a lot more important, but they're crucial here. You do not want to poke someone in the face, right? You want to be, and there's brings up a lot of other questions, which I'm not going to talk about today, but there's safety and there's also perceived safety. It's not just enough to actually be safe. go like this, and I stop right in front of you, you're not going to like that, right? Especially if you don't have motor control over your body. So that's kind of the funny, kids being kids, but this is really, we need this in robotics, the notion of verification. But it's complicated because people are complicated and have different abilities. So I'll go back to this. So I have the mathematics-based techniques, I have specification, development, and verification. And I'm just going to give this, let's see what I'm doing. And I want to kind of revisit this definition in the context of the way I think about formal methods for robotics. So here we have this notion of specification. So I'm gonna, if there's anything you remember from this talk, is specifications. We must have specifications when we build systems. We need to be able to have some language to talk about what they do and why and what we want them to do. But when you think about the robots moving around and falling, it's not enough just to have the specifications of what we want to do. It's always over some abstraction of the system, because I can't really have a full mathematical description of a robot interacting in the world with people. I just do not have that. So the question is, how do I create this kind of abstraction, these kind of taking the essence of what I need to deal with in a way that actually translates later on to something that can compute over and control. The other thing here is, again, there's a few themes that are going to come up again and again. Abstractions can also be, you can think about these as the basic building blocks that I can compose together to create the behaviors that I want or to verify and so on. In terms of words that I use, you've heard Florian say I use synthesis, so I kind of develop synthesis techniques. So the idea here is, given a specification, given some constraints on the system, can I generate in a correct by construction, so automatically generate code, system, structure, whatever, that satisfies the specification. So that's a question of synthesis. And finally, there's a question of verification. And verification, when I was a PhD student, when I presented my work at some conference, someone comes up to me and says, yeah, you can't verify it. What happens if a meteor falls on your robot? So, okay, verification might be not the right way to think about this. I can't guarantee that the robot will always behave as I expect, because I'm modeling certain aspects of it, not other aspects. But the tools that enable verification enable things that are actually very useful. So falsification. Under what conditions will I fail? Will the robot fail? Can I start reasoning about that? Feedback. What kind of specific feedback can I provide about the behavior of the system that I can use these tools to basically, instead of saying, I failed, rather saying, if the door was open, I'd be able to do this. Things like that. And repair. So this kind of goes back to the abstraction. I'll give an example of what I mean by that. But, yeah, I'll give an example. Okay, so what do I want to do now? There's going to be a few papers that are kind of, I guess, captive audience, get a jolly Asian look. Anyway, this is one of the papers that we did. So there's annual reviews of control robotics and autonomous systems. I was on the editorial board for a while, no longer there, but it's a once-a-year journal that publishes invited review articles. And there's a bunch of really, you'll see me kind of show a few of them. This is one that we wrote. This was in the first volume. And it talks specifically about synthesis and abstraction and specifications for robotics. So we look at different things there. But what I want to do in the next few minutes, I want to basically look at these different boxes that that I'm showing, and I want to show you examples of things that we've done using these techniques. I'm not going to go into detail of any of the techniques. I'm more than happy to have a conversation afterwards. But right now, just to give you what do I mean by abstraction? What do I mean by verification? What do I mean by synthesis? What do I mean by specifications? So if I talk about, okay, so now we're going to focus on specifications, abstraction, synthesis, feedback and repair. So I'm kind of ignoring the verification aspect for now. How many of you have seen temporal logic before? Awesome. Okay, so there's an increase over time in the spaces in which I give talks. But I always have a slide on temporal logics. So this specification language, I want to have some mathematically precise way to capture what I want my system to do. And there are different ways to do that, but one kind of, I would argue, fairly useful way is using what's called temporal logics. And I want to show you two temporal logics today. So the first one is linear temporal logic. And the idea here is I have symbols, I have propositions that are either true or false. I always give the example of me where I am in the world, right? So Hadas in Toronto is a proposition, it can be true or false. Hadas in Ithaca is a proposition, it can be true or false. Currently the proposition that Hadas in Toronto is true. Hadas in Ithaca is false. Agreed? Agreed. So now we can start doing propositional logic. You can do and or and all these things that you've seen in the past. But if the truth value of the propositions changes over time, now we can start saying things like, eventually something will happen. Eventually Hadas in Ithaca. Yeah, because, you know, your family won't be happy. Always Hadas in Toronto. Probably not. Okay, that formula is going to be false, and so on. So I can start doing things that kind of look at the evolution over time. And you can see how this can be translated to robot behavior, right? Eventually, I want to reach a goal. Always, I don't want to hit an obstacle. If I see a person, I want to stop. All these things can be captured using this kind of temporal logic formula. But the main thing here is that I have these symbols, and they represent something in the physical world. So they have to be grounded into something in the physical world. But the logic itself is over discrete things, discrete time, discrete actions, skills. We'll come back to the skills again and again. So what can you do with LTL? I want to show you a few things that we've done with LTL. And okay, so what's the idea? Here, you can take an LTL formula, you can take some constraints on the system, and you can generate a control for the robot that is symbolic, but then is mapped back to the continuous. So the symbolic represents some abstraction of the system, and by looking at the sequence or looking at some fine state machine, I can basically create the actual control. So what did we look at? We looked at, this is just a few examples because I want to show you different things that we can do. Top left, modular robots. This was a collaboration with Mark Campbell at Penn and Mark Campbell at Cornell, 2 marks. The idea there is we have these modular robots. Each one of these squares, these 10 by 10 by 10 centimeter squares, has 4 degrees of freedom, but it also can connect to other modules. And you can create larger robots with different actuation capabilities. So what we did there, the abstraction, was shapes and controllers for these shapes. So a shape can have multiple gates, multiple motions that it can do. And we can attach the behavior, we can attach to each configuration gate pair properties. And then those properties were the symbols over which we wrote specifications. So for example, in this example, the idea was and everything that you'll see with synthesis, you can write a controller, you can manually write a controller to do it, for sure. The whole idea of synthesis is moving the abstraction, if you will, higher in terms of how I specify what I want the robot to do and what code do I need to write to implement it. In this case, we could run different specifications. And in this case, this reconfiguration was done, again, ×8, mind you. The configuration that was before, I couldn't climb stairs. So I had to change the configuration, drop something off, go back. So really the task here was look for something pink. So the perception here was very, 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 in terms of objects, was simplified. We had a camera on top. We had one looking on top and kind of a RGBD camera looking around to map the environment. But the whole configuration was fully autonomous based on the specification that we wrote, which was go look for an orange, for a pink area and drop something off. So that's kind of what the modular was. The top right is going to be a multi-robot situation. Here, each robot has its own specification, its own task. So the blue robot is going to the blue arrow, the orange robot is going to the orange arrow. Each one of them is separate. They share an environment, but they don't know anything about what the other robot is going to do. The only thing they're assuming is that whenever they're in one of those regions, they're going to be the only ones in that region. So if another robot is currently occupying the region that they're in, there's a problem. So what you'll see here is that we start executing, and then this work was kind of autonomous negotiation of conflict, if you will. So they share parts of the specification, just the specification, just the formula representing what they're trying to do. They share that, and then they kind of re-synthesize their own behavior to accommodate the other robot if needed. So you'll see kind of it's again sped up. This was in the aircraft 2015. Yes, there you go. Okay, so again, sped up. Now, I'm not saying that it's going to do it in the most efficient way. It's definitely not doing it in the most efficient way. So the orange one is getting out of its way, but going all the way around instead of just backing up. But this is fully autonomous in the sense that we wrote a specification for each one of them. We put them in the same environment, and they negotiate that separately. Bottom left is some work. We talked about this. I talked about this with some of you. We had some work on going from natural language to this specification. Now this predates LLM world, so it was still learning based. So we learned from language to LTL formulas to templates. And the nice thing about that work was also we could recognize assumptions that the person didn't say but are required for the actual execution. So again, this is kind of, well, I'm going to skip that, but the abstraction there was, the reason I want to show this is A, we kind of connection to natural language, which these days looks very different. And the fact that the way we're mapping the symbols to the robot behaviors, it basically scales. So you can pick up something, you can drop something, and so on. So that's my abstraction. And finally, let that go. Finally, in this case, we're thinking about what does it mean to do swarm behaviors. So now I don't actually care about the individual robots. I care about the overall swarm behavior. And here the idea of the specification was we wanted the robots to distribute into these three. We wanted to eventually, robots to show up here, and then we want them to distribute here. The yellow one here is a dynamic obstacle. That's being controlled by my student. And the whole point here is to show I can write a specification, a high-level specification. I can automatically generate these subswarms based by color. You can see that they have different behaviors, and automatically execute that, even in the presence of a dynamic obstacle that's kind of messing up the things. So why am I showing you all these 4 videos? Mainly to show that once you have an abstraction in place, you can do a lot of things using these basically the same techniques. So roughly speaking, they're using the same techniques underlying, going from a temporal logic specification, generating autonomously and automatically generating the controls for these systems in a way that is guaranteed to satisfy the high-level behavior as long as my abstraction is right. Okay, so you have to have this correspondence between the discrete abstraction and the continuous system. If that breaks, everything breaks. Yes?
Does this have any implications for long horizon tasks that could be solved by task and motion planning, for example?
Great. So I very often have to respond to reviewers in terms of how does this relate to task and motion planning.
Yeah.
So it's very similar. So it's actually me and Will. Will Thomason.
Yeah.
Who was my student. I'm losing him. Actually, in the middle of writing a paper comparing the two, because the 30,000 feet view, we're trying to solve the same thing. The way we're solving it is very different in the sense that for people who don't know what task and motion planning, typically task and motion planning, what it does is you have a description of actions you can do in PDDL, which is a planning domain description language. So you have actions, they have preconditions, postconditions, and then you kind of go back between the symbolic and the motion planner to try to solve kind of longer horizon, more complicated things beyond the motion planner. Right? So if you want to basically clean up clutter on a desk, right? That could be a task in motion planning. So there's a little bit of nuance which I'm happy to go into later on, but for now, task in motion planning is very good when you have complicated motions and you have a clear kind of notion of symbolic goals, right? So you have actions, typically you have a goal, right? Or a single goal. And then you have this kind of back and forth with the symbolic and the continuous, the motion patterns. For the synthesis stuff, it is better at the longer horizon constraints. So do this, but don't do that. If this happens, then that happened. It doesn't quite. You can do both in both ways, but the task and motion planning the more complex tasks don't fit that well with the task of motion planning. And for the synthesis, because I'm using these abstractions, the really complicated motion planners that I need to, I mean, I can use motion planners, but then I lose the guarantees. So here if I have these abstractions and they hold, I have guarantees over the behavior. If I have to clean clutter off the desk, I'll use a task of motion planner. If I have to run a robot and have it basically be getting instructions from multiple people and look at any conflicts in specifications and do this and then do the other thing, and I would probably use the synthesis. So it's a little nuanced, but it's an excellent question. It's roughly in the same space. So these are with LTL. I have a discrete abstraction of creating these building blocks that I can compose from LTL. For something that's not quite as satisfying, because these are continuous systems. And when I talk about LTL, there's no notion of time. I can abstract time by putting a timer and having like an extra proposition that tells me when time has elapsed, but it's really clunky. If you have things that are timed, if you have deadlines, not the best logic to use. So a different logic, which I think, how many of you have seen STL? Oh, a lot less. Okay, but we like STL, right? Yeah. So STL, the idea there is, now I'm looking at continuous signals. And these continuous signals, I can write predicates over these continuous signals. So I can say, for example, I can write a function that either evaluates a number that's either positive or negative. If it's positive, I consider the predicate to be true. If it's negative, I consider the predicate to be false. For example, my distance from Tim, that's my continuous metric. That's my continuous signal. And I have a predicate, my distance from Tim is greater than 1 meter. Currently true. If it was to come and stand on you, it would be false, which I'm not going to do because, that's just weird. Come on. But now I can write things over continuous signals, given that I have these predicates. And I can write it over time intervals. So now I can have deadlines. I can have timed operators. So eventually within the next 5 time units, or time units, whatever you want to tell me what it is, I want to reach the door. Always in the next 10 minutes, I want to make sure my camera is pointed forward, and so on. So you can think about kind of these things. So these are timed, and just to show you kind of what we've done with that. Again, as an example, we kind of took STL, changed it a little bit to be able to have a little more discrete structure. So I can say I can react to events that are Boolean. And then, I want to say one more thing about STL, but I'll get back to that. And then what we can do is we can control robots and change the specific. The main thing about synthesis, it's not that given a task, it's not that I can't write it, I can't program my robot to do it. Of course I can. But if I want to change something, the change requires me to change a sentence. It doesn't require me to go back and change, whatever, my coding, my parameters in my code, everything like that. It's moving it to a higher level of abstraction in terms of interacting with the robot. So in this case, what we use this for, actually I did an HRI study, human robot interaction study. Top was in simulation because, of course, we started doing this and the pandemic hit, so everything was in simulation. So we did that in simulation. The bottom is the same, it's kind of an evacuation scenario. We were trying to see different robot strategies, how they would affect the evacuation rate and satisfaction or compliance of the person. So we had that robot in a simulator, so a Unity-based simulator, but fully autonomous in that simulator. Then we went last year and actually ran it on an actual robot outside in one of the less nice buildings in Cornell. Not my building is gorgeous. So this is, again, we tried two different behaviors, and the idea here, the only thing we had to change was basically the specification. So one of them, the robot is following, the other one, the robot is kind of initiating and trying to kind of guide the person. Now, the other thing that STL has, which is really nice, is that when you think about logic formulas, you typically think about the values to true or values to false. I don't know if you typically think, but if you think about a logical formula, it values to true or values to false. STL also has quantitative semantics in the sense that I can have a number that indicates how far I am from satisfying or violating the specification. So if I want to So if the number is positive, the formula is satisfied. If the number is negative, the formula is violated. But how much it is, I can tell based on this metric. And we can use that to do a bunch of different things. And I'll mention it a little bit later. So in this case, when you can use it also to give pre-failure warning. So it doesn't really matter what's going on here. There's a bunch of robots moving around. This is event-based SDL. This is a robot that's autonomous. This is a robot controlled by David, my student, my former student, my graduate. And this robot needs to get here within a certain amount of time, but also maintain a distance from this robot. So you can tell that if this is an adversary, this needs to stop. But I'm trying to, but the longer this one is not moving, the less likely this is to be able to reach the end in a certain amount of time. So I cannot guarantee that the robot will be able to satisfy its task because I have no control on parts of it. But what I can do using these continuous metrics is tell you, okay, you're about to violate the specification, or, and this comes back to the feedback. So verification, for me, going from provably correct, verified, all that, more towards, okay, I can't verify everything, but I can start thinking about when can I say it's verified? When can I provide feedback? And specifically, what is the thing that's going to go wrong with respect to the specification? And that's kind of what these things allow us. Okay. In terms of the last thing I want to talk about in terms of our prior work, in terms of, well, not quite, but in the context of giving you an overview of the things that we can do, we can take some of the verification and actually also synthesis techniques and do both feedback and repair. So what do I mean by that, by repair? So repair is something we've been doing in the last few years. The idea there is, remember we talked about abstraction? I have some abstraction. I'm required to have I need an abstraction to be able to write a specification over what I want to happen. What happens if that abstraction is not quite right? Or it doesn't necessarily follow what happens in the physical world? I want to be able to repair. More specifically in this context, what I'll show you in a second is, assume I have a bunch of skills. The abstraction is skills, and that's kind of where it comes closer to PDDL, because it has preconditions, it has both conditions, but still in the context of LTL. I have these, I can define these skills, and then I can compose them. I can define these skills, and I can say, okay, I want this to happen, I want the robot to do these following things, and what it will give me back, I'll tell, okay, do this skill, do this skill, do this skill, do this skill, or do that, and so on. What happens if I don't have a skill that will satisfy my task, right? I'm just missing a skill. Either because I'm putting extra constraints on the task, maybe I can go this way, but now there's an obstacle there, but I don't have a skill to go down, right? So how do I try to find these missing skills? So that's one of the things we're leveraging the formula, the specification, and the synthesis algorithm that failed to find a set of skills to satisfy the task, to find a definition of a missing skill. And that's kind of what I'm excited about, because that goes back to actually fixing the abstraction to some extent. It's not going to give me more symbols, but it will give me more possibilities of moving between symbols. So this is, our examples tend to be very simple, so bear with me. So the idea here is I have a robot that's moving, this is a cup, this is an obstacle, it needs to move some things around, the cup is, this is all under Vicon, so we're not doing any perception in this case. And then there's a cone here, and I have a few skills. So the skills that I have, the robot can move, so it moves from the right side to the left side, those are the two move skills. It can pick up an item, but it can pick it up only, so it can pick it up, okay. It can pick up the cup and place it in a certain place, and pick it up and place it in a certain place. It can move an obstacle. And it's going to go a little far, a little fast here, but really what's going on here is that, sped up. Now, it's actually encountering a situation in which it needs to move this, the only skill it had was to move this obstacle here, but it can't move it there. So it needs to create a new skill on the fly. So it creates this new skill on the fly, and there are a few examples of skills, we'll see in a second, this is less easily explain. But really, it's moving through this area back and forth. Now it's not allowed to move through the cone. So now what you'll see is that removing the cone, and now again, it needs to, it's not that it's difficult, right, in this case, to look at what the solution is, but the thing is it didn't have that skill, and now it automatically finds that skill, repairs the task, and moves on. And the question here is we can repair the task symbolically, but we want to execute it physically. So this kind of back and forth, sometimes you can give symbolic suggestions. Oh, you know that for a second. You can sometimes give back and forth. You can sometimes give a symbolic suggestion that is physically impossible, like teleport, right? So we have this kind of back and forth between the physical and the symbolic to be able to use the physical to limit the symbolic, and the symbolic to guide the physical. So kind of repairing these. So I'm kind of excited about that. All right, so that's the FM, which is the formal method for robotics. The other FM, what do I mean?
Foundation model.
Foundation model, yes. So I'm using foundation model very loosely as learning, which is, it's been very interesting to see in the last 2 years, I would say. I don't know, it's kind of exploded in the last 2 years. Which has been very exciting. So, last year I was on sabbatical. I spent time at Toyota Research Institute. And Toyota Research Institute, if you see this, they're really pushing on the manipulation, well, the robotics division. They have a bunch of different things. They're trying to create what they're calling the large behavior models. So the idea there is you have a lot of data, you use diffusion policies, you learn skills. Okay? So I'm going to go with skills. But I didn't want to use TRI videos, so I'm going to use something else. There's a bunch of videos out there, but I wanted to show one video that you may or may not have seen. This is 1X. It's one of those companies. Pick up a sweatshirt. It's picking up a sweatshirt. I'm gonna let it run a little bit. It's not the full video. But you'll see that it was bring the sweatshirt to the meeting room. You'll see the command here, which is given natural language. And you have, pay attention to how it's cleaning up the spill. I love that they kind of, very cool on this. Pushing the chain. Okay. So let me start. I tend to be a skeptic, and I tend to kind of start. I mean, the good is obvious, and the bad needs to be said. That's kind of my personality. So I'm going to fight against my own personality. To say that there are some things here that are amazing, right? So first of all, this is real time. This is one shot. There's no editing. This is kind of, and this is all from data, right? So they collect a lot of data. They run these things. So there's a lot of promise, and there's furthermore, like we picked up a sweatshirt, which. Okay, maybe that, because it's still equivalent, but people have shown dexterous manipulation tasks or skills, I wouldn't call it skills. It's exciting, I'm a skeptic, it's still exciting. However, someone told me that instead of saying but, say and, it's very exciting, and, it really is. And what you see here is a bunch of disjoint skills, right? I can pick up something, I can drive, I can drop something, I can push. So you can kind of see where I'm excited about this, in the sense of, there's a bunch of skills that I assumed are coming from somewhere. I can abstract this physical system to do these skills. And some of them, motion around the environment, as we were talking, motion like 2D navigation, we know how to do that, right? We definitely under Vicon. We know how to do that, we can create that abstraction easily, done in the lab. But like folding a shirt, hurt. Peeling a cucumber, how do we do this model-based? I'm not quite sure. So there's a lot these kinds of techniques open up a lot of possibilities for these skills, right? The other thing that is important to me, with the context of verification, context of synthesis, is how repeatable are these? Is this going to work tomorrow? Is it going to pick up, I 100% believe that this was one take. It all worked. But also, this is a very nice environment with nothing in it, basically, right? There's no clutter here. This does not look like my home. Definitely does not look like my office, unfortunately, right? So there's a bunch of things there. So the things that I'm excited about is it looks like there's a pathway to create these really cool skills in a way that I would like to use to compose. The challenge that I have at this point in time, it will change, I hope, is How do I define what a skill is? Yes, I have a natural language, but how do I think about that kind of in a more general way? And can I actually use these, right? Can I actually use these? Are these repeatable? Are these, why does it fail? It will fail sometimes. Does it fail because the lighting is slightly different? Or does it fail because now instead of a black sweatshirt, I have a pink sweatshirt? I don't know. So the time I spent at TRI, I read a lot of papers around these foundation models, and I know I'm being recorded, but still, a lot of the papers that I read, I was not impressed by the evaluation. The papers are super cool. The things that people are doing are super cool. They're not evaluated in a way that will make me confident or even understand when I should or should not use them. So I wrote a paper, which I'm going to plug here, which is Robot Learning is an Empirical Science, Best Practices. And it's on archive. Hopefully it will be published at some point. And the idea there is, again, my perspective is that I do not want to build these things. I actually don't want to do that. That's not my research. I don't want to do that. I want to use whatever people are doing. Very smart people are spending a lot of time and energy and thought in terms of creating these models. I would love to use them, but I don't know if I can use them yet. So this is my soapbox. This is part of my soapbox here. Evaluation. So if you're creating these models, pay attention to evaluation. If you're reviewing papers that suggest these models, please pay attention to the evaluation. A few things. Some things that show up. The main thing in the metric that's being used is success rate. Very often, papers don't actually say success. The success rate is basically a percentage of successes out of total number of attempts. The total number of attempts is very rarely written. So you don't know 90% of how much? Of 10? Which, talking to people, apparently 10 is a number that is used. I'm sorry, talking about actual hardware experience. Simulations is a different story. More metrics, more discussion about initial conditions, more discussion about when does it not work? I want to know when it doesn't work. It doesn't mean that your algorithm is not good. It just lets me calibrate when I should use this and why I should use it. Okay, off my soapbox, but I like this. So I promised synergy. So John's not had to leave, but he was, when I sent him my abstract, he was like, yes, synergy! Sounds right?
Yes.
Yeah. Sorry, John. I see a lot of synergies between, you think about, formal methods for robotics, and you think about learning, especially the things that are going on, kind of the pace that things are going at right now, and you think of it all, it seems like it's two different fields, but really I see a lot of promise and a lot of excitement in a synergy of what formal methods can bring to the learning community, what learning can bring to the formal methods community within the context of robotics, because robotics is such a hard problem. So I want to give you a few maybe parting thoughts in terms of, and one example of something that we actually did, of where I see the connection and what I'm excited about. So, safety and learning. So these are two papers from, actually one of they view, so these are two different papers, two different review papers on two different topics, but ultimately what they think about is safety. So the bottom one is, as I'm learning, as I'm using reinforcement learning, right? How do I do that in a safe way? So this mainly, giving it a very 1 second thing, is thinking about the actions that I'm allowing, how am I allowing my system to explore? That's kind of putting safety constraints there. The other one, the safety filter, is given that I have a system, how do I add something on top of it that prevents it from doing stupid things? Right? So there are different techniques. And both of these, the specification itself is typically, I'm exaggerating, but typically a safe set. So which states are safe, which states are not safe. And that is a specification. It's not a very complicated specification, right? I don't want my system to collide with something. So the set of collisions is bad, the set of non-collision is good. But you can kind of think about also continuing these ideas to more complex specifications, which is what people have been doing. So this is just a Google search of temporal logic and learning, right? So a lot of reinforcement learning, and interestingly, these are the top hits, and most of these are coming from researchers that are actually in the formal methods side of the world. For these ones. So the idea here is reinforcement learning, but the reward function of the temporal logic formula. So you can have a slightly more complex, hopefully, specification. There's a lot of challenges and a lot of interesting things there. So using specifications as the definition of what it is that you want to learn is kind of an interesting direction. But the things that keep coming up are specifications, because we have being able to articulate what that specification is helps later on with composition and so on. Verification, falsification. So verification system is guaranteed to satisfy my requirements. Falsification is, here, look at an example of which it failed. Falsification, typically easier than verification, both are useful. So when you think about these learning systems, and especially if you think about the larger ones, okay, so there is work on verifying neural networks, and it's cool work. You can do very small networks. It's very often kind of a very common way to think about verification of a neural network is if you're close enough, if you're within a ball of the input, if you have an input and an output, if you're within a ball of the input, are you going to be within a ball of the output? That's kind of it works, it makes a lot of sense for some domains. I think for me, for vision, it becomes a little more murky, kind of what does that mean? I care more about verification of the full system. So if I can verify one neural net, what does it tell me about the composed system? So there are a bunch of questions. I mean, it's a really fascinating research direction. Yeah, but another way you can think about, and this is kind of, I like this tutorial that we did. So this is Sanjit Seshria out of Berkeley. They have a system in which they're really employing what's called probabilistic model checking, or stochastic model checking. So you have a simulator, you're running it, and you get probabilistic guarantees. And the nice thing about this is you can get falsification. Falsification is really interesting because then if you have a real, if you have a specification, you run your system, you find an execution that falsifies your requirement, then there can be one of two things. Your requirement was wrong, the system's problematic. And both of them are good information, right? So it's kind of a way to keep assessing your system in a way that, for a system that can't fully model check or fully prove this kind of probabilistic model checking. One thing that we did, with a former student of mine, is using this STL robustness. So if I have an STL specification and I want to calculate the probability of that specification holding for my system. So for linear systems, we can do this in a nice way. But what happens if we have a system that was learned? So I actually have a black box. So now I can use this robustness metric to guide my sampling towards falsifying situations. So here's an example. Every time I give this talk, every time I talk about this work, okay, what do we do? We have this is a simulator. We learned a controller that's supposed to pick up a block from the table and lift it above 0.5 meters. Why? Because that's what we want to do. The idea here is I have a black box. The controller itself does not matter. We train it through reinforcement learning. I'm not trying to say it's the best way. It is not supposed to be always successful. I don't care, because sometimes I get the question about, but did you use the parameters for the reinforcement learning? That's not the point. The point is I have a black box controller. And I have a specification for this black box controller, okay? And then what I can do is, and here, the uncertainty is where the block is on the table. So what I can do with this, with these kind of techniques, by taking into so one thing I can do to verify my system, or to try to verify my system, or to probabilistic verify my system, is to sample, right? So I can do Monte Carlo sampling, and this is what I did. I'm going to sample, the sampling of positions of, so I sample a position of the block, I simulate, and I check yes, no, about the specification. Black points are failures, red points are successes. So I've got failures here and red. Our work here is actually sampling, but biasing the sampling towards regions that are less likely to be successful. So you can see we started here, but then it kind of moved towards these two regions. So we need a lot less samples to be able to find falsified systems. Now, here, we can both calculate the probability of failure. So this is the probability of success, right? So it's kind of different in this case. But the other thing we can do is we can also sample the behaviors. And it turned out in this example, it was kind of interesting, because these failures corresponded to these three, all three of those basically dropped the block. So they either dropped it low, dropped it high. This one, the robot didn't lift its arm more than 0.5. Now, why it didn't? I don't know. I don't care. It's a black box. Could we train it better? Of course we could train it better. That's not the point. The point is now you can start sampling from clusters of failures to see different semantic failures of the system, which is kind of cool. All right, the following thing that we already talked about. The final synergy that I see is the repair. It's still thinking, it's not really what I was thinking. Is the repair, right? So if I have a task that I want to do, and I'm missing a skill, I can use this kind of formal methods to figure out a description or a requirement on what skill I'm missing. And then what really I want to do, I want to go learn it. I don't want to start necessarily, maybe I'm taking a control that I had and I'm tweaking it a little bit. Maybe I'm fine-tuning something to have the exact behavior that I want. But now this back and forth between the specifications, the symbolic, the ability to figure out what is it that I'm missing, and from the learning perspective, being able to train a controller, to train a system that does that, this back and forth is really interesting. As long as I can say something about the learned controller, right? As long as I can know what the failure modes could be, as long as I can, there's a bunch of kind of questions there in the interface I find really interesting. So that's the final synergy that I would like to show. Now it's frozen. I'm just going to continue. I'm going to have it. I remember this was the last kind of well, the next slide was the repair. We talked about that. So take home. What I wanted to kind of leave you with. I want to leave you with, there's a lot to be gained by thinking about formalizing robotics, using formal methods for robotics. It is not a silver bullet. It will not solve everything. But there's the notion of thinking about specification, thinking about specifications that are computable, that you can transform into something else. Thinking about verification, thinking about how do I start assessing my system with respect to a property that I'm trying to figure out. And the connections that I see to learning, I think are very, very exciting. So that's kind of, I wanted to leave you with specifications, synthesis, verification, and learning. All these four things, okay? I have a really nice slide with pictures of my students, and this picture at TRI, and two of my students, a guy who did this work, and David, who did the event-based STL work. They're both like a foot taller than me. And they both graduated at the same time. So I have a picture of me in my robes, and both of them next to me, and both sides of them next to me. I actually have the students at Cornell, when we did the graduation, were very happy. They were very amused because we graduated the same year. I had to set up step stools, so to hood them, I brought a step stool and stood on that, and that was the step stool was a hit. So I had to bring it back the next year, even though the two that graduated they're not that tall. I didn't need it for that, but that was really funny. So I have a picture of that. So basically, kind of acknowledging the students who did all the work, and I have also a picture of the people at TRI that I worked with this year, which was very exciting and very nice to work with them. And with that, and a frozen computer, I will say thank you. How do you set questions? Yeah.
So on this slide, it's great because the frozen slide is the one I wanted. Aren't you making the assumption that if the cube is close to another location you've tried, then the behavior of the robot will be similar? No?
No, no.
Okay.
What I'm doing is I'm sampling from my noise. My noise here or my uncertainty here is the location of the block. So it's a very simple, because we don't have any noise in the either. And then as I'm sampling, I'm looking at how far I am from satisfying the task, this robustness, and I'm trying to start shrinking down the robustness, or trying to sample in directions in which the robustness becomes lower. Because robustness, the more positive it is, the more, if it's positive, my specification is satisfied. If it's negative, it's violated. But the more positive it is, the more space I have for it to fail. The kind of, the more, well, for lack of a better word, the more robust it is, right? So what we're trying to do here is we're trying to sample in a way that we go down the gradient of the robustness metric.
And is it continuous, or?
It is continuous. It is not necessarily differentiable. Pretty, yeah. Because what's going on here? So really, the thing that's going on here is that you have these different predicates. And in these predicates, so you have different timings, so you can have different timings, and you can have different predicates. And it could be that one predicate is becoming closer to being violated, but something changes, and then you jump to a different predicate that's close. So it could be that you have these kind of jumps, but it is going to be continuous. I think it's going to be continuous. Yeah. So yeah, we can kind of go down that route. So for linear systems, we know how to do that in reject. For linear systems and Gaussian noise, we can do this in a rejection-free sampling. So I sample, and I'm always going to kind of go in the direction of falsification. When we start talking about black box and nonlinear noises, then we have to do some other things. Yes?
Yeah, also on this example, so let's say you took these failure locations and then you continued to update your black box controller underneath, right? And what would you end up with when you kind of addressed all of those situations? Would you be able to tell if there were more situations with this method? Would you be able to tell if there were more situations that maybe basically I'm asking, can you...
Can I have a 100% guarantee that it's correct? Is that what you're asking?
How do you know your falsification is comprehensive, I think?
Okay, so the question is, I don't know if, I'm just going to repeat in case there are people on Zoom. How do I know that my falsification is complete? I don't, it's probabilistic, right? So I'm estimating the probability of failure of this specification given this system. So as I prepare, and this specific method is better than Monte Carlo for rare events. If it's not a rare event, then Monte Carlo is fine. You don't need the extra complexity that we have here, which I didn't talk about, but it's more complicated. But the idea, if you have very, very few failures, it will give you a better indication because you're going to be you're basically kind of trying to seek them out to some extent. If you start adding them, and then if I can't find, I'm going to let it run for an hour and I can't find any falsifying examples, doesn't mean they don't exist. But it's probably going to mean that it's very unlikely for them to exist. But yeah. And this falsification is exactly, you were mentioning kind of this feedback of taking a falsifying example, putting it back into the training, and I think that's another place that it's, this combination of falsification, specifications, learning is very powerful. I'm going to go, I don't know, mostly I don't know the names.
Thank you very much for the talk. I was wondering, so you, in the STL example, you kind of showed that the robot was trying to, reach a destination while kind of maintaining a certain distance.
Yeah.
So it's quite interesting, kind of like quantifying the probability of failure. But how do you deal with conflicting, like entirely conflicting specifications, where, and maybe even going further, where they're equally bad? Like for example, hitting, like the red herring that's always used in autonomous driving is, will you hit the grandma or the baby, right, in a critical situation? So how do you deal with these kind of conflicting specifications?
Okay, so the question is about conflicting specifications. So I'm going to answer that in a few ways, and it could or could not, may or may not actually answer your question. So we're going to go. So first of all, once you have a specification, it's a logical formula. You can detect conflicts, right? You can detect that it's not consistent formula. So some of the things that we've done in the past was also to, ahead of time, look at the specification to see if it's going to fail, or if it's conflicting. And there are tools coming from more of the SAT solving community, and there are other tools you can use to pinpoint to unsatisfiable cores, one of the words that are being used, to figure out what is the part that is conflicting. So you can kind of ahead of time even tell, you know what you're asking me to do is impossible. Okay? Then there's the question of, as you're going, monitoring what's happening. So there's the notion that there's conflicting specification. I'm asking the robot to leave the room and stay inside. Can't do that. So in the context of synthesis, so that's already something that we can detect ahead of time. There's the question of, okay, so conflicting specification. There's also the question of, because there's conflicting specification and there is an execution that violates the specification, which is not the same thing. Specification being inconsistent, you can detect quickly. The system at some point being kind of starting to falsify the specification, that's the problem, right? And for that, there's the notion called runtime verification, that people can create monitors to detect when things are going to go wrong and when things have gone wrong. Or if you have this robustness, sometimes when things are going to go wrong. So that's kind of, you can kind of anticipate, or not necessarily anticipate a failure, but say, no, if this happens now, I'm going to fail. So you can kind of start thinking about that. The grandma versus baby hitting the thing, to some extent, in the self-driving, and again, I'm not a self-driving car researcher, I know you all know way more than me. There is some specification. Whether it's automatically written and synthesized into the controller, I doubt it, but there is a requirement document that someone wrote. There is, even if nobody wrote a requirement document, people look at failure modes and say, okay, it really should have done that. So hopefully it's documented in a way that's consistent and verified, or verified with, or hopefully it's written in a way that someone looks at it. There is risk analysis, and there's a lot of techniques to kind of deal with that, right? But my soapbox of specifications is to explicitly reason about those things, and not do this in a kind of, oh, really, we should have tuned this way, we should do that way, right? Because then you go into the system, I'm not quite sure what it's doing, and then maybe I can monitor it to see that's respecting my specification, but yeah. And then you have the notion of safety filters and things you can put on top of it to fix it. So, but a little bit roundabout. Specification inconsistency, that's not the problem. The problem is the system not satisfying the specification and figuring that out as early as possible. Yes?
Great, so I have a bit of a high level of abstract, if you will,
Yes.
questions, so I apologize in advance.
Not at all.
But my question has to do with the symbolism and abstraction of, like, that's kind of like a precondition to doing these kind of logical specifications, which I'm a huge fan of. But you had a slide that said that robot learning or maybe machine learning is an empirical field or something like that. And so I think a lot of roboticists definitely believe that robotics is also a purely empirical field. But for coming up with symbolism, I'm wondering, do you think there's another kind of source of knowledge that we need to be able to say, like, yes, like position versus velocity, that symbolism is right for a mobile robot or not? Or is there some sort of guidebook to inspire the researchers to come up with this?
For the abstractions. So the question was, is there a correct abstraction? That's kind of what you're asking, right? Is there one, or maybe more, right way to go from a physical system, from whatever, the molecules moving around in space, or atoms moving around in space, to the behavior that we want? And I don't think so. I think it's very task dependent. I think it's system dependent. I think there are good guidelines, right? There has to be a simulation relation, if you will, if you use the correct terminology, but there has to be correct grounding of whatever symbolic representation that I have, right? I have to be able, if I do something symbolically, and we're all doing things symbolically ultimately, right? It's all symbolic at the end. But the more coarse I want this symbol to be, the more I'm putting requirements on the actual physical implementation. And that kind of played around with how coarse how large my vocabulary is in terms of symbols, like how coarse the abstraction is. The coarser it is, the easier the symbolic, the harder the implementation. The more fine-grained the symbolic, the easier it is for the physical, the more computationally expensive it becomes for the symbolic, maybe I'm not able to compute. So there's this kind of, beyond even what am I trying to abstract, even the level of abstraction is something that, and I don't have an answer for that. I don't have a good answer. I don't have an answer for that, because I think that's one of the engineering questions, right? How do you think about systems? But I want that question to be front-loaded. When you're building a system, when you're creating these, the empirical science part, I actually don't think roboticists think, I don't know if the rest agree, I don't think they're roboticists, I don't think about robotics as an empirical science. I think about robotics as, does anybody think that robotics is an empirical science?
Purely empirical?
It's both. Okay, both. Well, I think the ML side right now of learning skills is empirical. Because it's too big, we don't understand it. We have to treat it like a science. We need to treat it like something that nature created. Granted, it's not nature. Granted, there are Nobel Prizes about it, but there's that. Something that it's an artifact.
Phenomenal.
Say again?
It's phenomenal.
So it's an artifact. It's an artifact that exists and that is changing. And we want to explore it and see what can we learn about it. So in that case, or in this case, from an engineer's perspective, how can I use it? Right? When can I use it? When should I use it? So that's the empirical side. That I agree with you, but that's the empirical side. Yeah, I have no good answer for how to abstract what is the right way to abstract. I can tell you what is the wrong way to abstract. If the symbols are not grounded well, it's useless, right? But that's not too surprising. Yeah. Fine.
I have a couple of questions.
Yes.
So one is about your evaluation paper.
Yes.
You were advocating for A/B testing amongst, a host of
Yes.
solutions.
Yes.
And I don't think the robotics community has thought a lot about A/B testing, which is what you said in your paper. I'm wondering if it's always realistic for roboticists to be expected to do A/B testing in every single type of experiment.
No, absolutely not. Absolutely not. So the question was about A/B testing. A/B testing, if you don't know what that is, it's basically blind. So you have multiple different policies, and it's blind to the reviewer, to the evaluator, and they run kind of one after another. This was very specific for if you're telling me that policy A has a success rate of 80%, and policy B has a success rate of 90%. I want to know that you did A/B testing, and you didn't test everything on one day, and one policy on one day, and the other policy 2 weeks afterwards. Because these things are not sensitive sensitive to initial conditions, sensitive to lighting conditions, sensitive to whatever. This was written very much with a kind of behavior cloning view of the world. Okay, so I don't know if this is going to be controversial or not, but I would argue that a lot of times in robotics, what we're doing is not so much experiments, it's demonstrations, right? So it's not like we're not trying to evaluate a hypothesis. We're trying to demonstrate that our system works. In that case, A/B testing doesn't mean anything, right? I don't need to do that because this is the system I built. I want to have good evaluation metrics to say, okay, this is good or bad, but I don't need to compare it to something else. But the things that are happening now, and especially from the foundation model point of view, is like, this architecture is better than that. But this architecture is better than that has to be A/B testing because you're doing a relative argument here. So in that context, A/B testing should be happening, right?
So in the context of manipulation, that makes a lot of sense.
Mm-hmm.
What about in the context of navigation, where these experiments are, hours long, or you drive for half a day or longer? Don't you need a very large number of experiments in order to be able to make that comparison effectively at the end?
But if you have,
or is A/B testing better suited for short-term experiments that you can do in the manipulation side?
So the question is about the A/B testing, whether it's good for long-term experiments versus short-term experiments. I think it's really what we're trying to say. If you're trying to say that A is better than B, do A/B testing. If you're saying this system that I built can do this, this, and this, and these are the metrics I'm evaluating, the thing is the comparison. If you're saying this is better than that, you have to compare them in a blind way, right? So I think right now, a lot of the conversation around this policy is better than that policy are very short horizon things. They're not very long horizon things. And here I am on my largest soapbox of really complicated tasks. Don't learn them end to end. Why are you going to learn them end to end? Learn the skills, compose them. Okay, that is my strong opinion. In which case, the skills themselves is the A/B testing. And then the composition will be whatever technique you feel right. Or maybe you compare things, but then it's not that hopefully the comparison is more nuanced in terms of not success rate. But rather, these are the pros and cons of this technique. These are the pros and cons of that techniques. If you're talking about a technique with respect to itself, I don't think there's a need for A/B testing. But a lot of the literature you see now in terms of the foundation model stuff is baseline, ablation, which is, that's the right way to do it, but you have to do it in a way that you're very careful about how you experiment. Otherwise, it's meaningless. If you don't match initial conditions, right? And I don't think, by the way, just to be very clear, I don't think there's any malice. I don't think anybody's trying to cheat at all. I think it's a culture thing. And a lot of these experiments came from more of the vision and kind of video and image processing, where it's a lot easier to control for what. I mean, you have a set of images. You're going to use that, right? Running a robot today, or right now it's beautiful and sunny outside, versus tomorrow when it's going to be, in 2 days, I think it's going to be really rainy. The lighting is going to be different. The image is going to look different. It's going to be different. So that's kind of where you can. That's where if you want me to understand, or if you want me to believe that A is better than B, you need to be very careful about how you show that comparison, more than anything else. Question back.
What about using simulators for testing them and keeping real robot for demonstration? Because I think in simulators it would be fair to compare different robots.
Great.
And keep the hardware and the real robot for demonstration because it's more expensive, it takes time.
So the question is using simulation for comparing different policies, and then using the real hardware for demonstration.
Yes, and then for evaluating a real robot, we could create a competition workshop where the robot comes and then the task can be realized. It's very hard to compare otherwise real systems.
Yeah. So I think, okay, so there are a few things here. Yes, in simulation you can compare much easier. I am yet to be convinced that the simulation actually corresponds to the same comparison of the real world. That's not clear, right? Because we don't know that. So if we want to have, and the way we're thinking about this is more kind of in terms of ranking, right? So if A is better than B in simulation, does that mean that A is better than B in the physical world? Maybe, maybe not. We don't know, right? Physics is not, simulators have, if we're able to say that the ranking in simulation is preserved in ranking in physical, yes, absolutely, simulation would be the great thing to do. And then kind of show things on the physical. We don't know that yet. Beyond the sim to real gap, even the evaluation simulation, what does it mean for simulation, for evaluation in the physical? Because ultimately, I care about the physical, right? So simulations is a powerful, wonderful tool to do things quickly. But that last gap, so maybe it's a good way for me to screen things that are really bad and get rid of them in simulation. But again, if they're bad in simulation, doesn't mean that they're bad in the physical? I don't know, right? So, and then to your point about competition and stuff like that, at this point in time, it's very hard. Everybody has their own hardware, their own control stack, because also, even if you have a learned model, the control stack that actually runs the robot is going to be different. And that matters, right? That really matters. You're not running it, you're not running the voltages to the joints at the level of the. So it's exciting to see how fast things are going. It's a little nerve-wracking to see how fast things are going. It's a little kind of, what I've heard from students mainly, it's very stressful for them in terms of how fast it's going. In terms of, am I going to if I don't have 4 papers a year, is it, it's like, I definitely as a student did not have 4 papers a year, not even close to that. But the expectations down, so it's a little bit kind of, this really fast-paced thing is typical for a young field. It will stabilize. It will stabilize in a good place. It will stabilize when we start to understand a few more things. We can use it for more things. But right now we're kind of just at the transient, which is exhausting. Exhausting for me, and I'm just looking at it, right? I'm not even in that really in that field. Yes?
For the repairing problem, what is the setup? What are the inputs and outputs?
So for the question is for the repair work, what is the setup, inputs, and outputs? So we're assuming we have symbols. So those symbols correspond to abstraction of the environment. For example, I have a cup is in this region, or robot is in this region, that kind of abstraction. We also have skills. And the skills are the things that change basically the environment. In addition, we might have additional environment events, for example, an alarm, or some keyboard input or something like that. And what we're trying to do is we write a high-level specification over the symbols of the environment, so where the robot is, where the objects are, and we try to synthesize. And if we can't find a controller, it doesn't exist, now what we do, we look at the structure of how we're synthesizing, and we're trying to find a new skill. So a set of, I should mention this, the skill is defined as, it has basically, it's written in LTL, so not in PDDL, but roughly speaking, it has, you can execute the skill under these conditions, so it's a precondition. And if you execute the skill, this is what's going to happen afterwards, so it's a postcondition. And what we're trying to find, we play around with, we try to modify the preconditions or modify the postconditions, or both, to find a new skill that if I had it, would make the whole symbolic problem solvable. So I'm going to do this, oh, now use the new skill, now use this, now use this, now use this. And then we take this new skill and we try to physically implement it. So we have different techniques to do that. Some of them, there's some kind of, we've done some things with the dynamic motion primitives that you can change them subject to LTL specifications, so we can kind of play around with that a little bit. But that's kind of a thing we're still looking at, kind of how do we go back from the symbolic to the physical and back and forth. So that's the idea. Yeah.
If you are different symbolic solutions, you will also specify which one to do.
So right now we're just putting one, but one of the things we want to look at is can I connect some continuous metrics into or some things from the physical into an ordering of preferences on the skills. We have not done that yet, because it's a little bit tricky to think about what does that mean, right? But right now we're just spit out whatever solves it. It's the first thing we'll spit out. Yep.
All right. Let's get the plane landed here, and let's thank Hadas.
Yeah.
There's food on the back, and feel free to mingle